Bismillah Rahmanir Rahim. Assalamu alaikum. Welcome to ASTC. This is Cambridge A Level Mathematics 9709 Mechanics. So today we will be solving some exam style questions which are related to momentum. So let's start with question number 1. Each of the two wagons has an unloaded mass of 1500 kg. One of the wagons carries a load of mass mkg, okay, and the other wagon is unloaded, okay. The wagons are moving towards each other on the same rails, each with a speed of 2 meters per second. Okay, so each one of them has a speed of 2 meters per second, but in opposite direction because they are moving towards one another when they collide. Immediately after the collision, the loaded wagon is at rest. Okay, and the speed of the unloaded wagon is 3 meters per second. Find the value of m. All right, so let's say that if we draw a wagon. Okay, let me copy this. All right, so let's say that this is the loaded wagon. So the mass of this will be 1500 plus mkg, right? Because it is also carrying some mass. It is carrying some load of mass mkg. So this will be 1500 plus mkg, and the other one is empty. Okay, it says the other wagon is unloaded. So that means that it has nothing in it except it has its own mass. So this will be 1500 kg. Both of them move towards one another with the speed of 2 meters per second. Then it says immediately after the collision. So this is the situation before collision. Okay. Now after collision, what happens? The After the collision, the loaded wagon is at rest. So that means v is equal to 0 over here. So this is the loaded one that comes to rest, and this one we don't know. Or actually we do know. It says that the speed of the unloaded wagon is 3. Okay, my bad. This will be 3 meters per second. All right, find the value of m. So this is the situation after collision. So it is always helpful to draw a quick diagram like this. Okay, on the top you can represent what the situation is before collision, and at the bottom you can represent what is the situation after the collision. All right, so we'll start with the principle of conservation of momentum. So that will be total initial momentum equals total final momentum. All right. So the initial momentum of the unload of the loaded wagon, this one is 1500 plus m times the initial velocity. So that will be 1500 plus m multiplied by the initial velocity, which is 2. Okay, another thing that we must specify is the direction. Okay, we must specify which direction are we taking as positive. So I'm taking the right hand side to be positive. Now for the second one, the initial momentum of the unloaded mass of the unloaded wagon will be 1500 times minus 2, because you can see that the movement or the motion is towards the left. So if I'm taking right hand side as positive, that means left hand side will be negative. So this will be plus 1500 times minus 2 equals, now the final momentum of this one will be 1500 plus m times 0. Let me pull off all of this a little bit back. Plus 1500 times. Now the velocity, it says immediately after the collision, the loaded wagon is at rest and the speed of the unloaded wagon is 3. Okay, now here it hasn't specified that is the speed 3 meters per second towards the left or towards the right. So we will just consider this to be towards the right. Okay, because if it comes to rest, right, if now think about it, if the loaded wagon, okay, this one, if this one comes to rest, that means this one must have rebounded. Otherwise, if it would have continued moving to the left, then this one cannot come to rest, right? So that's why it makes sense that this truck or this wagon has rebounded. So therefore, we can draw the direction towards the right hand side. So now I can write this 1500 times 3. So now let's calculate. 2 times 1500 will be 3000 plus 2m minus 3000 equals, okay, so this one, this whole bracket multiplies with 0. So this becomes 0 and this becomes 4500. Okay, so this 3000 cancels with this 3000. So we have 2m equals 4500. Therefore, m is equal to 4500 divided by 2. So that gives us 2250. Okay, so this is the mass that was loaded onto the wagon. All right, let's move to question number 2. A spacecraft of mass 40,000 kg docks with a space station of mass 160,000 kg. Okay, so spacecraft has a mass of 40,000 and a space station has a mass of 160,000. The spacecraft is traveling at 202 meters per second immediately before docking takes place, and the space station is traveling at 200 meters per second. All right. The docking is modeled by two particles moving in the same straight line. Okay, so they are moving in the same straight line that collide and coalesce. So that basically tells us that they are moving in the same direction. Okay, so let me copy that. All right, so let's say that this one is our spacecraft and this one is the space station. So the mass over here is 40,000 kg and the mass over here is 160,000 kg. A spacecraft is moving at speed of 202 meters per second. So you can say that this is your initial velocity, and the space station is traveling at 200 meters per second. So this is the situation before collision. Now, basically, our collision in this sense will be the docking, right? The docking that takes place. And we know that the particles will coalesce. So that basically means that we have two particles which are joined together. Okay, so the word coalesce basically means that the particles have now been joined. So now this is 40,000 kg. This one is 160,000 kg. And now together they are moving at the same velocity, which is v. Okay, so we don't know what is this v. So you can just write v meters per second. And definitely because both of them are moving to the right, so their subsequent motion after collision is also bound to be to the right. And we'll take right hand side to be positive. So now the question is calculate the exact speed of the spacecraft and space station after the docking. So this is what we need to find, the value of v. So I'm going to write down total initial momentum equals total final momentum. Now you can also use some different wordings if you like. You can also say total momentum before collision equals total momentum after collision. So even that works fine. So here we can say the momentum of spacecraft will be 40,000 times 202. So definitely you'll end up with some big value. So you can write in standard form or you can just uh, write them the way they are going to appear. Then the initial momentum of space station will be 160,000 times 200. So 160,000 times 200 equals total final momentum. Here the masses will be added. So we have 40,000 plus 160,000, and together they are traveling at velocity v. So now let's simplify them. So we have 40,000 times 202. So this will be 8.08 into 10 to the power, or let me just write them down as it is. If we want, we can write the final answer as a standard form. So we can just write this 808, and then we have, all right, so this is 8,080,000 plus 60,000 times 200. So that will be, so we have six zeros. All right, 40,000 plus 160,000. So that will be 200,000 V. Now, when you add them up, so here what I can do is, because if I want to avoid writing everything in calculator again and again, I can just, in a single step, I can divide by 200,000. So now I can just write them once in my calculator. All right. Now be careful about how many zeros you're writing. Okay, sometimes you are very quick in plugging in the values in the calculator, and you miss out one or two zeros, and then it'll just mess up the whole answer. Okay, so be sure to double check what you have put in your calculator. So we have 808, and then we have four zeros. All right, then we have 32, and then six zeros, and then we have two and five zeros. So when I work this out, I'll end up with v is equal to 200.4 meters per second. So this is the combined speed of the space station and the spacecraft. Now this is an exact value, so I don't have to write down in 3SF. Okay, if if the calculator gives you the value in exact form, so you have to write in exact form. Okay, you don't have to unnecessarily round this to 3SF, because it is already an exact answer. All right. So let's move to the second part. This was part A. Now, part B is calculate the total loss in kinetic energy during the docking. Total loss in kinetic energy. Okay. Now, understand one thing. If I want to work out the change in kinetic energy, so naturally that would be the final kinetic energy minus the initial kinetic energy. Okay. If let's say that the value of delta ke is negative, so let's say that we have minus delta ke, and these are the values that we have. Okay, if I want to make this positive, right, how can I make this positive? If I want my delta ke value to be positive, so what I'll have to do is I'll have to shift this to the other side and bring whatever is here onto the left hand side. So my value, or my formula, sorry, will become initial kinetic energy minus final kinetic energy. Okay, now the question is, why did we get a negative delta ke value? Because this was a loss in the system. There was a loss in the system. You had a greater value at the initial stage, and the final kinetic energy was lesser than that. So that means there was some loss in kinetic energy during the journey. All right, so that loss can be represented by this formula directly. Okay, so that means I don't have to write delta ke. I can directly say loss in kinetic energy will be the initial kinetic energy minus the final kinetic energy. Okay, now because the negative part, okay, has already been taken into account by the word loss and by the reversal of the formula. So now I need to find out that what was the total initial kinetic energy and what was the total final kinetic energy. Now, total initial kinetic energy means the initial kinetic energy of the spacecraft plus the initial kinetic energy of the space station. So that will be we can say half mv square, or you can say all right, we already know the formula of kinetic energy. I'll just write the formula here once. Okay, and then we can just plug in the values. So first of all, I'm going to look for the spacecraft. The mass is 40,000 and its speed was 202. So we have 40,000, speed is, or velocity is 200 whole square, plus half into 160,000, and this one was 202 whole square. Let me double check. Okay, I've written them the other way around. Sorry, my bad. See, that's why it is important to double check, because when you're doing your examination, students sometimes get so involved in the question that they don't even read the question a second time. Whereas what my advice is that even once you're done with the answer, you have reached the final answer, read the question one last time, that is this what the question is asking you. Because usually when the question is of 5 marks or 6 marks, you just get carried away into doing the question, and maybe you just forget what the initial question was. Or maybe sometimes if the question tells you to give your answer to 3SF or to two decimal places, you miss that part because you did not read the question once you were done with the question. Okay, so that is why it is important to keep note of that. All right, so let me grab my calculator. So that will be 202 whole square. So this gives us 81608, and then we have four zeros, plus half into 160,000 times 200 whole square. So this gives us 3, 2, and then we have, how many zeros are these? We have 4 and 4, 8 zeros. Okay, so we have 8 zeros. So when I add this, this will be 81608, and then we have 4 zeros. So this becomes 401608. Then we have two zeros. Okay, all right, so that will be joules. Now the total final kinetic energy will be their cumulative mass, which will be 40,000 plus 160,000 times their velocity, which we worked out to be 200.4 meters per second, right? This was their combined speed. So let me work this out. So we have half into 200,000 times 200.4 whole square. So this turns out to be 4016016000. All right. Now you see the reason why I did not write them in standard form is because if I would have rounded them off or something, then I would lose the exact value. Okay. So that's why in some cases it is better that you work them as they are. All right. And then later on, if you want, you can write your final answer as is in standard form. Okay. So this will be, now the loss in kinetic energy will be the initial kinetic energy minus the final kinetic energy. All right, so let me write this down. So this will be 401608, and then we have four zeros minus 4016016000. All right, so let me work that out. All right, so let me subtract this. All right, so we get 64,000 joules, or we can also write this as 64 kilojoules. That's your final answer to part B of question number 2. Okay, all right. Let's move to question number 3. Two particles of masses 0.2 kg and mkg are moving towards each other and collide directly. Immediately before the collision, the 0.2 kg particle has a speed of 4 meters per second and the mkg particle has a speed of 2 meters per second. Okay, so let me draw this out first. Okay, so this one is 0.2 kg and this is mkg. So we don't know the mass of the second particle. They are moving towards each other. Then the speed of zero point 0.2 kg particle is 4 meters per second and the speed of kg particle is 2 meters per second. Then it says in part A, given that both particles are brought to rest by the collision, find the value of m. Okay, so this is before collision. And if both the particles are brought to rest, that means that after collision, their final velocities will be 0. Okay, all right. So again, we'll apply the same concept. Total initial momentum equals total final momentum. All right. So the first case will be 0.2 times 4 plus m times minus 2 because we are taking right hand side to be positive, whereas mkg, the particle mkg, it's the particle of mkg mass is moving towards the left. So this will be plus m times minus 2 equals 0 plus 0 because the final velocity of both of them will be 0. So the final momentum is going to be equal to 0. So here we have 0.8 minus 2m equals to 0. So 2m is equal to 0.8. Therefore, m is equal to 0.4 kg. All right. So that was part A. Let's move to part B now. Now it says given instead that after the collision, both particles move at a speed of 0.5 meters per second. Find all the possible values of m. Okay, so let me copy down this diagram first. Okay, now it says that both of them have a final velocity of 1.5, sorry, 0.5 meters per second, but they haven't specified that what is the direction, right? So now if you imagine this scenario, there could be three possibilities. Okay, let me list them down. So after collision, there could be three possibilities. The first one could be that both move to the right. Okay. The second possibility could be that both move to the left. And the third possibility could be that both move in opposite directions. Both move in opposite directions after the collision. All right. Okay. So these are the three possibilities that we have. So dealing each one of them one by one. So here again we have total initial momentum equals total final momentum. So the initial momentum will be 0.2 times 4 plus m times minus 2 equals, now here we have 0.2 times 0.5. So if we are assuming that both of them move to the right, so both the velocities will be positive. So this will be 0.2 v plus, sorry, v is 0.5 that we already know. So 0.2 times 0.5 plus m times 0.5. Okay, now simplifying them, 0.2 times 0.5, that will be 0.1, half of 0.2, and this will be 0.5 m. Okay, so we can collect the like terms. So we have 0.8 minus 0.1, and we have 0.5 m plus 2 m. So we have 0.7 equals 2.5 m. Therefore m is equal to 0.7 divided by 2.5, and that will be 0.28 kg. That is the first possible value of m. Second possible value can be if both of them move to the left, then this part remains the same, the initial part remains the same. However, here now we have 0.2 minus 0.5 plus m times minus 0.5. Okay, so this will be 0.8 minus 2m equals minus 0.1 minus 0.5 m. So now this minus 0.1 comes to this side, so we have 0.8 plus 0.1, and 2m goes to the other side, so we have 2m minus 0.5 m. So now we have 0.9 equals 1.5 m. M is equal to 0.9 divided by 1.5. So in this case we have 0.6 kg. Okay, that's the second possible value of m. Now the third scenario is that both of them will move in opposite directions. Okay, so again the first part will be the same. So we have 0.2. Now if both of them move in the opposite direction, that means 0.2 kg, this is the one that is moving to the left, so this will have a velocity of minus 0.5. M will move to the right, so it will have a positive value of 0.5. So this will be minus 0.5 plus m times 0.5. 0.8 minus 2m is equal to minus 0.1 plus 0.5 m. Then again this goes to the left hand side, so we have 0.9. This goes to the right hand side, so we have 2.5 m. Therefore m is equal to 0.9 divided by 2.5. So that will be 0.36 kg. Okay, so this is the end of question number 3. All right, and this is also the end of our lecture. In our next video we'll go through some more questions. Okay, so stay tuned. Till then, take care. Assalamu alaikum.